Okay, so we'll start at Dalton. We'll kind of breeze over Democritus and stuff, but Dalton was the first scientist who proposed a model for the atom. So actually said this is probably what the atom is like, making a model. He suggested that the atom was a tiny invisible chunk of matter, and this is what we called, like in Science 10, we said that was like the billiard ball model. Billiard ball model. However, with the development of the cathode ray tubes and the discovery of cathode rays, the model of the atom needed to be revised. So the video didn't explain this part. They just said what J.J. Thomson kind of discovered, but this is how he learned about the electron. So we're going to try and understand this experiment in a little bit more detail than we did in Science 10, and so that we can understand and do calculations similar to what he did. So a cathode ray tube consists of a set of parallel plates, or electrical plates, placed inside a glass tube that contain a gas under low pressure. When a voltage is applied across the parallel plates, the gas in the tube will glow, and a cathode ray will be emitted from one of the electrodes. So it will be like a ray, like a beam. J.J. Thomson did a lot of work with his cathode ray tubes and observed some interesting properties of the cathode rays. So one of the things that he saw is they would travel in straight lines under this kind of situation. They could be deflected both by magnetic and electric fields, therefore cathode rays could not be EMR. So it's like they have a charge, they could be pulled up or pulled down. Okay, so if you brought like a magnet close to the cathode ray, the cathode ray would either kind of curve in toward it or go away from it if it was attractive. It didn't matter what the cathode ray tube was made out of, so it didn't matter what type of gas or anything, but the properties of the emitted cathode rays remained the same. So Thomson applied an electric field using a set of parallel plates, so an external one. So this is an external electric field, and here's the actual cathode ray. And he noticed that the rays would always bend toward the positive. Okay, so here's the ray coming through, and if there's an electric plate there, it would bend up. Okay, so here, that's the cathode ray. Thomson discovered that the cathode ray were actually tiny negatively charged particles. What would those particles then be? A tiny charged particle that's negative? An electron, yes. So this is the electron. So the cathode ray is really a ray of electrons being emitted from the gas. Okay, the gas has been excited, and those electrons are released. And so it's like almost like a beam of electrons, okay? So with the discovery of the electron, Thomson revised the model of the atom to what is referred to as the raisin bun, or plum pudding, or cookie, or I don't know, whatever you wanted to call it. Not plum pudding. Have you ever had plum pudding? Who eats plum pudding? I don't know.
Did you say the cathode ray goes towards the positive plate?
Yes. Yeah. So it's like,
So
here it's coming out like this. This is the cathode ray, and it gets deflected up.
I thought your black line was the cathode ray going away.
Oh no, sorry. I was just pointing to that stream there thingy. That's the cathode ray. I'm pointing to it. Yeah. Thank you for clarifying. That's the cathode ray, and it's being deflected up. Yeah, good question. I didn't mean to make that misconception. All right. With the discovery of the electron, oh, I already did that. The atom now had components. Instead of just being a chunk, an indivisible chunk. So it's made of components, positive, negative, okay? Thomson continued working with the cathode ray tubes to try and determine the charge to mass ratio of an electron. So it's like finding the Q over M, charge per mass. So it's looking for that fraction or looking for that ratio. What's the ratio like of charge to mass of an electron? Okay. By applying an external magnetic field, okay, so now he's adding a magnetic field, okay, to the cathode rays traveling in a straight line, Thomson noticed the cathode rays bent in a circular path. And he measured the radius of the curvature. So remember, so this is kind of going back to our forces and field stuff. So if, say, there's an electric plate being put in there, or a magnetic field, sorry, and we have the movement of, like, say, our electron is our thumb, it will be forced, so it starts going in that circular pattern, right? So remembering back to the forces and fields, this is kind of what is going on, why it's going in a circle. So, if an electron is going in a circular path under a magnetic field, we can say that Fc is equal to Fm. Okay? The assumption that we can make when it's traveling in circular motion in a magnetic field. Really important assumption for these kinds of questions, okay? So if you hear any of the questions say the electron was traveling in a circular path in this induced magnetic field, or in the magnetic field, you can make this assumption, okay? So now we can kind of look, okay, he was looking to figure out charge to mass, so we need a Q and we need an M. So we're going to expand these to include Q and M in them. Okay, so look at your formula sheet. Go back to the forces and field kind of stuff. That would have been, under our electricity and magnetism. So let's say which Fc Fc can be mass times acceleration, or centripetal acceleration. So then I think, okay, my AC, I need my mass included in there. So, yeah. It's hard, we can't tell everything from what we are looking for right now. But the one that we're going to choose, just for showing you, is the mv squared over r. Maybe I'll just use a different color. M times v squared over r. Okay? And let's look for our Fm. What has Q in it? We're going to use our Q times B perpendicular. So if I equal these to each other, and what I want to do is I want to make a formula where it's Q over M is equal to blah, whatever's left over. So let's rearrange this so that I have Q over M is equal to, and then everything else. So looking at this at first, we have V on the top here and V squared on the top on this side, so I can cross those off to make life a little simpler. Now, the way I think about it is, okay, my Q is on top on this side, I want to keep it that way, or you can just cross multiply your fractions to organize it. So you could do like M times V is equal to Q times R times B perpendicular. Well, you want to get Q over V. So you want to get Q like by itself. So I'm going to bring R and B perpendicular to the other side. So I have M divided by V is equal to R times B perpendicular is equal to Q. The last thing I need to move over is my M, right? So I'm going to, this is all times by M. So to get rid of M on this side, I divide by M, and I can divide by M. So I'm left with B over R, B perpendicular is equal to Q over M. So being able to make the appropriate assumption, bless you, and rearrange the formula will be important for these questions. So let's do the first example where we have to make assumptions and use these types of formulas.